Hi everyone, welcome back to our ISC webinars. It's nice to see everyone here today. Hope you are all doing well. So today we have a very exciting topic by Assistant Professor Alexander Ling from the Center of Quantum Technologies on how quantum technologies are affected by a bit about quantum technologies and how it can be affected by space weather. So I hope everyone is having a good week so far. And as usual, we will be recording, we will be recording this webinar and we will be sharing it with all the participants who have registered after. And also if you have any questions along the way, please feel free to drop it in the Q&A box. Try not to put it in chat so that we don't lose track of it. Try to put it in the Q&A box so that we can keep track of it and then make sure that your questions hopefully get answered. But yeah, so otherwise, I will hand it over to Professor Ling to take over.
Hi, Jillian.
Hi. Yeah, we can hear you.
Okay, that's great. So good afternoon, everyone. It's a real pleasure to be here. The Center for Quantum Technologies is very happy to be a supporter of this year's Space Challenge because we are starting to see the deployment of quantum systems in space. And we are very much concerned about the longevity of these technologies in the space environment. So we're actually quite excited to see, what the Space Challenge will turn up. So a brief introduction on myself. I am a principal investigator at the Center for Quantum Technologies, or CQT, in Singapore. And I'm also a professor of physics at the Department of Physics at NUS. And what I do in my research life is that I look at how we can deploy quantum communication technologies around the world. The technology has been making a lot of progress over the last 2 decades, and it's ready for deployment, outside the laboratory. And we have been working in that direction over the last 10 years. And one of the milestone achievements that we have done in Singapore is that we've packed some quantum communication devices into a very small satellite, a nano satellite. And you can actually see on this page over here, the deployment of the nano satellite as it comes out of the International Space Station. And so in today's talk, I'd like to share with you the motivation for putting these devices in space, and also to talk a little bit about what we have observed of how space weather interacts with the devices and why it's necessary for us to develop an even better understanding of space weather. Now, as I go along in my talk, I will try and find some natural stopping points where we can take a break and we can look at whether there are any questions in Q&A. So, if you have, anything you want to ask, just type it up over there. Okay, and we'll try and see whether we can handle some queries along the way. Okay, so, and one more note to Jillian, sometimes the internet connection might be a bit unstable. So if I start to break up, just feel free to jump in and let me know.
Sure thing.
Okay, very good. So let's get started. And, why are we so excited about quantum technology today? Well, essentially, the main reason is that we have developed a very good understanding of how to encode information inside very small physical systems. And when I say very small, I'm talking about systems that obey quantum mechanics completely. So if you're using your computer or your cell phone today, you probably know that we are processing information using bits or conventional bits. And these are typically magnetic memories inside your cell phone or computer, or if you're transmitting this information, they are encoded as pulses of radio signal or light pulses if they're going down an optical fiber. Now imagine looking at a light pulse, which is going down the optical fiber, right, which is composed of millions and millions of particles of light, but still being able to communicate when that pulse is composed of only a single particle of light that we call a photon, right? So when you are talking about encoding information inside such an individual particle, you actually start to get access to more interesting ways of manipulating the information. Now, a conventional bit of information, right, can store, either a 0 or 1 in a distinct state of the system. So for example, you're talking about memory in your hard disk. It probably has to do with whether the magnetic field of that particle is pointing up or down, right? But if you're talking about storing the information, the 0 or the 1 inside an individual particle, then we have the ability to store not just a 0 and a 1, but perhaps a 0 and a 1 at the same time, or any weight of zeros and ones, right? And this continuous, flow or tunability between the state of the data being a 0 and a 1 is actually very powerful, and is the building block of why we can actually do very interesting information processing today with quantum technologies. Now, if there's only one takeaway message from this talk today, is that you should be aware that we are now in the realm of producing quantum bits of information, or what we call the qubit, right? And so in this slide over here, you're looking at a conceptual idea of what a qubit is. It means that you can, if you look at it in one direction, it's a 0. You look at it in another direction, it could be a 1. And so the qubit is actually what's enabling all these exciting advances. Now you can form qubits using any individual system that obeys quantum mechanics. In this picture on the right over here, you're looking at a very cold electrical circuit, right? And you cool electrical circuits below a certain temperature, they become superconducting. So this is an example of a superconducting qubit that has been developed here in Singapore, right? And on the bottom picture over here, you can see this row of bright dots, right? Each of these individual dots is an individual atom, right? So over here, what my colleague has done, he's got about 2 dozen of these individual atoms, and he's actually trapped them, and he's actually taken a picture of these atoms, and you can actually see that these atoms are all giving off light, and that's why he can actually identify how many atoms he has trapped. And we can also form qubits out of individual particles of light. And in this picture over here, you're looking at one of the more conventional ways in which we can generate qubits from light, in which we take a blue laser, we pass it through a special crystal, and this crystal actually interacts with the blue laser, the photons inside the laser beam, and splits each photon into 2 photons of lower energy, and one of them is going to the left and one of them is going to the right. And you can tell that they are of a lower energy because the color of the photons is different. Now, this is very exciting, because now that we can manipulate qubits, we know how to make them, we can manipulate them, we can put them together. This is leading to a very wide variety of possible applications. Very often we talk about how this distribution of quantum particles of light, the photons, can be used to improve communications and security, such that your communication signal will become hack-proof, right? So that an eavesdropper with a very powerful computer will not be able to intercept and decrypt your messages. On the other hand, if you put all of these qubits together, you can actually, and you store information inside them, you can begin to manipulate the information. And so this actually allows you to build a computer that is fundamentally different from what we have today. And so this is the field of quantum computation. And of course, if you have a quantum computer, you can use it to simulate many things. For example, new drugs, new chemicals. And this is actually expected to be one of the major applications of a quantum computer. And finally, if you have individual control over the systems, they're actually really sensitive to the environment. So you can actually build, quantum sensors that can, for example, tell you whether, there are clouds overhead. Imagine that you have a device inside a basement somewhere with no windows, no access to the outside world. But just by measuring the property of the quantum system inside that room, it can tell you whether, there are clouds overhead, or whether it's the weather is changing. And this is actually, something that is very useful in terms of very sensitive measurements. So these are all the broad domains that we are actually interested in. But I want to shift the focus a little bit today and talk about quantum communication, right? And the question would be, why should you care about quantum communication and security? And essentially, the main reason is because of this guy in this photo over here. This is a scientist, a quantum physicist by the name of Peter Shaw. And in the 90s, he discovered an algorithm which said that if you have a quantum computer, right, you can actually do something known as the factorization of the products of prime numbers. And this algorithm is known as Shaw's algorithm. It's named after him. Now, this is actually a little bit of a curious question. Why should we care so much about the fact that a quantum computer can factorize products of prime numbers very rapidly, right? And the reason is that almost all our existing encryption today, the way we derive privacy and security in our communications, is built on top of the ability, or what we think is the inability, of a conventional computer to factorize these numbers. So all the encryption and data privacy algorithms that we are using, for example, when we are trying to buy something online, we go and use the HTTPS protocol, right? So that we can actually send our credit card details across the internet. All of that relies on the fact that the product or this prime numbers, how should I say it? The multiplication of prime numbers is not something that can be factorized very easily by a conventional computer. Now, what Peter Shaw said was that a quantum computer would get exponential advantage. So this means that if you think that the security you enjoy cannot be broken by a conventional computer in 20 years, with a powerful enough quantum computer, this advantage will go away in maybe a few weeks or a few days. So this becomes quite worrisome. And in fact, there's a host of other quantum algorithms that people are studying. And if you go to this website over here, it's called the Quantum Algorithm Zoo, and you can see how many different other types of quantum algorithms that people are proposing for quantum computers. Now, coming back to security concerns, right? Since Peter Shaw's days in the early 90s, when he talked about a quantum computer, it was at that time considered a curiosity, because no one had actually demonstrated a quantum computer that worked. But that's different. Nowadays, you can actually get access to multiple quantum computers on the cloud. IBM was the first company to do that. They actually have been studying quantum computers for decades. And a few years ago, they placed their quantum computer on the cloud so that now anybody can get access to it and learn how to do programming on a quantum computer. And as we are moving along, we're seeing more and more companies doing this. And that's on the hardware side. On the software side, there's lots of progress being done as well about how to actually make use of noisy quantum computers, right, in order to break the algorithms that underpin our communication security. So for example, on the left over here, there was a recent paper, right, that talked about how you can break the RSA 2048-bit algorithm, which is very commonly used, right? In only 8 hours, you have 20 million qubits that are not very good, they're noisy. Now, of course, 20 million sounds like a very large number of qubits today, because at the best we can do today is maybe to put together a few hundred qubits. If you want them to all work together, maybe you're talking about a few dozen qubits. But what we are concerned about is that there's an exponential growth in the process. Lots of countries and companies are now investing in how to actually make better and better quantum computers. So there is, an understanding that one has to think about how to actually protect against this. So there are two main ways that we can actually be quantum safe in our communications. And one of them is to, find newer algorithms, right, that could be resistant against a quantum computer. They're typically known as PQC, or post-quantum cryptography. And there's actually a worldwide competition right now, coordinated by the National Institute of Standards and Technology in the US, to try and find candidate algorithms. We have to keep in mind, of course, that these algorithms are only suspected or believed to be resistant against a quantum computer. And one should not put all our eggs in one basket and claim that the PQC approach is the only approach. This is because research into quantum computers is still nascent, right? It's still ongoing, and we don't yet know what is the full power of a quantum computer. So there are concerns that even in the PQC approach, if you were to select and finalize on one or two algorithms, they could potentially be broken in the future. Now, the other approach that we can be, quantum safe is to use quantum physics itself. And this is a technology known as quantum key distribution, or QKD. Now, QKD actually has multiple flavors. Okay, there's many different flavors on how you can actually implement quantum key distribution. But one flavor that I want to introduce to you guys today was actually discovered by this gentleman on the left. He used to be the director of the Center for Quantum Technology in Singapore, and his name is Arthur Eckert. And Eckert actually discovered a protocol also in the 90s, right, in which you can actually use these qubits, right, to ensure communication security. And the flavor of QKD that Arthur actually came up with has to make use of a very fundamental property in quantum physics called entanglement. Now, for those of you who have been doing some background reading about quantum technology, you may be familiar with this equation over here at the bottom, right? This is an equation that expresses the state of two photons or two particles that share maximum entanglement. And the way to think about entanglement is to think of correlations. In this equation, if you look at it, there's 1 and 2. So these are actually labels that we give to two particles, right? And they're written as H or V. They actually refer to the polarization states of light. But for all practical purposes, we can think of the H as an arrow pointing up and the V as an arrow pointing down, right? And so what this equation is saying is that when you have two particles that are in an entangled state, what could happen is that if you measure one of them and you find that its arrow is pointing up, you can predict that its twin will also have an arrow pointing up in the right direction, right? So both of them would be pointing up or both of them would be pointing down. And this correlation will persist no matter how far apart they are. Now, the reason for writing this equation like this, where there is a grouping of HH on one side and VV on the other side, is that you need to ask the photons the right questions, right? If you ask them whether you're pointing up or down, right, and you ask them the same question, they will give you the same answer. And this is the takeaway message from this equation. And the way to generate particles like this is actually in this picture that you saw earlier. This is what's happening is, again, you have these blue photons interacting with this nonlinear crystal, right? And sometimes some of the blue photons get separated into the photons of lower energy. And then there's one that goes to the left, we can call that 1. And then there's one that goes to the right, you can call that number 2. And so if you ask the right questions to the photons, right, you will get the same answer. Now, I'm going to show you a little cartoon, right, of how this actually works conceptually. So let's go back, let's play this image. So imagine you have one of these light sources that can produce these entangled photons, right? And now you're sending them to far distant receivers. Let's call them Alice and Bob. And these receivers are asking these photons some questions. They're asking the photons about whether they are pointing up or down or whether they're pointing sideways, right? And the photons will then respond. And if you look at this diagram very carefully, you'll see that when their questions are the same, right, the photons will actually give the same arrow direction. And what we can do is we can identify an arrow direction with a 1 or a 0, right? And when you do that, you can actually have a subset of the string of signals where you get correlated numbers. Now, this is a random number that's correlated, and you can actually use that for your encryption, right? What happens if there's someone who's trying to tamper your system and then replacing the photons inside? when they do that, they're going to break the correlations, right? And they can, at most they can do is guess what the direction the arrow is going to be. So as they tamper with the system, sometimes even if you're asking the right questions, the photons don't actually give you the same arrow direction, and therefore your ones and zeros will have errors inside. And so at the end of the process, you also select a subset of the signals that you have received, and then you say, okay, what is the rate of error that I have, right? And so this error rate tells you whether there's an eavesdropper tampering your system or not. And so one can always do the statistics, calculate the error rate, and gain some confidence about the communication integrity. Okay, and so this is actually pretty important. Now, what I want to do is take a break here and see whether there's anything in the Q&A that people want to ask. So let's see Q&A.
Yes, we do actually have a question from Nikhil. Nikhil asks, does the quantum communication satellite launch communicate keys or information or both? What are the data transfer rates achieved, and how does Earth's atmosphere and the environment or space affect these rates?
Right. So, right. So we're jumping the gun a little bit. I'll talk about this in my next few slides, but essentially the quantum communication signal will distribute the photons, all right? And what you want to do is you want to measure those photons. And then any communications can make use of the secret key that's derived that way, okay? I see that there's another question. It says, when one tries to interrupt, would the signal collapse? So if you think back to that cartoon that I showed you, when the eavesdropper was trying to intercept the signal, what it does is it breaks the correlations, okay? And so in that sense, there is a collapse of the signal. But saying a collapse of the signal is not so interesting because the photons are still traveling. The energy packet is still going to arrive at the detector. But what's going to happen is that when the two receivers compare, right, whether the photons are pointing in the same direction, they're going to find all kinds of errors. And this is where they know that someone's tampering with the system. Okay. So I think let's stop here with the Q&A and let's move on. So in my next slide, I want to talk a little bit about the quantum channel. So this is a nice concept, right? We say that, okay, we have a fundamental building block by which we transfer quantum signals. We can actually, allow these correlations to exist at distant locations. And a very, convenient way to do this is to send the signals via optical fiber. Now, this works if you have, your receivers in a relatively short range, for example, across the size of Singapore. But if you want to, link up different locations on the globe, you're going to find that direct linking doesn't work very well. And the main reason is that optical fibers, as good as they are, they still have a lot of losses inside. So in the quantum regime, if you're sending an individual particle of light down a fiber, typically after 100 kilometers, that particle of light is either absorbed or scattered away. And this is the main reason why in conventional optical communications, we have something called a repeater. We take this large pulse, it attenuates in power and energy, and then it arrives at a repeater at a strategic location, and the repeater then measures this pulse and then regenerates a pulse to pass it on. Unfortunately, you can't do that in the quantum regime, right? Because if you were to measure the individual photon coming in, you'll be acting as the eavesdropper. You'll be measuring, its state, and you'll be disrupting the correlations. So we have not yet actually understood how to build a quantum repeater. And this is the main reason why when we think of quantum communications on a global scale, we are thinking of using satellites. And so, we have various, ideas on how satellites could actually be used. For example, you still take reference to that entangled source where you have a central light source distributing a pair of photons out. You can actually, put the light source on the ground and transmit one photon up to space, keep the other one on the ground, and now you have a link between the satellite and the ground station, or you could actually do it in the reverse, put a source of a transmitter up here and send the photon down and keep its twin on the satellite. Or you could actually transmit 2 photons down to the receivers at the same time. Of course, if you want to work with the third configuration, then you're going to need to be able to see the 2 ground receivers simultaneously. So it might work for a regional basis, but it probably will not work on a global scale. Now, you can also try and think of using the satellites exchanging these quantum signals so that their own communications between them can actually be quite powerful and can be quite secure. So this is the different aspects that we have, and these are ideas that's actually been tested and been developed. There are 2 quantum satellites I want to talk about. One of them is from our colleagues in China called MISIUS, right? And this is the one on the left. You can look at the internals of the MISIUS satellite. And the other one is Spooky One on the right, which is developed by my team here in Singapore. They have different objectives. Now, the MISIUS satellite was the most successful, or how should I say, the only satellite that has transmitted signals out of itself to a ground receiver. And so it's been used to demonstrate some of the primitives in quantum communication, like teleportation, entanglement distribution, and it's also been used to test out many of the building blocks of satellite to ground quantum key distribution. Spooky One, on the other hand, has a different objective. What we wanted to do was to see whether we could actually miniaturize the quantum devices so that they don't have to be so large, and whether they can actually be hosted on nanosatellites. So we're actually pushing the limits of what can actually be integrated between quantum technologies and nanosatellite technology. And then we found that because the nanosatellites are relatively easy to deploy in space, it's very good for studying low Earth orbit performance. So this is a cutaway model of Spooky One. And you can see that the quantum payload is in here. And you can see that it's at most covered by some solar panels. So when this thing is in space, it's not going to have a lot of shielding capability. And this is one reason why we are so interested in the idea of how do we do better predictions of space weather? How do we actually correct for the influence of radiation on the quantum payload if we can? Now, this is just a slide to show you that in order to put this quantum light source or the entangled photon source, we actually have from the top is a payload cover, right, to ensure that everything is light tight. And over here, this is the optical elements mounted on a piece of titanium. And all these components in here are actually listed on this schematic here on the right, which I'll come to in a minute. Now, in order to make sure that everything is sort of decoupled from the rest of the mechanical structure of the satellite, this entire experiment is mounted on some isostatic mount assembly. Now, you come to this optical layout over here, right? Remember, Spooky One is not yet ready to transmit signals out of the satellite because that would require a telescope. So what we're doing here is just to make sure that we can generate those entangled photons, right, in a very small package in space and detect them at the same time. So what's happening is that we have this blue laser diode over here that's passing through some nonlinear crystals, right? These are the crystals that convert the blue photons into the entangled photons. And then what we do is we transmit those entangled photons to 2 single photon detectors over here. And it turns out that of all the components inside this optical layout, we found that it's only the detectors that are the most sensitive to radiation in space. The laser diode itself is based on gallium nitride, so it's actually very resistant against radiation, both from protons and from ionizing radiation. Now, when we deployed the satellite in space, and this is a photo taken by the astronauts after they pushed Spooky One out of the space station, one of the first things we had to do was ensure that we understood what was the optimal conditions. Now, I don't know whether you would consider the Earth's, the eclipse time of a satellite is part of space weather, but in our opinion, it is. Because, when you have a satellite in low Earth orbit that's going around the Earth, for about 60 minutes, it's, absorbing energy, right? And then for another 30 minutes, it's in the Earth's eclipse. And so over here, this is a schematic where the shaded part shows the amount of time inside the Earth's eclipse. And this is very important because it tells you that the internal temperature of the satellite is actually, still increasing, even though it has now started to go into eclipse. This is because the amount of heat that's been absorbed by the structure is now being transferred to the rest of the internals. So we have to understand these things very well in order to operate the quantum experiment. So the first few days of any deployment is always spent, trying to understand how the satellite is spinning, which of its phases are being presented to the sun, so that we can actually have a better understanding of the rates of heating and cooling, and then to decide where we can turn on the quantum experiment. But essentially, what's happening is that we have been successful in doing this. And what we do is when we have these single photon detectors, we're detecting correlations, right? We have these two photons that are coming out of the source. They're going click at each detector, and when we're counting the pair of clicks that are correlated. And so typically what we do is, as we run the experiment, we look at how this correlated clicks would change, right? And we do a comparison between the shape of the correlated clicks on Earth and in space. And what we've done in Spooky One is we've shown that there's essentially no difference, right? The brightness, right, which is the amplitude or the rate at which these clicks are happening in space, is the same as on Earth. And the contrast of the curves, by which we can tell the quality of the correlations, is also essentially the same. And so for this reason, we believe that it is, mission accomplished. So after that, we decided to look at, what is the effects, the long-term effects of radiation on the quantum components. And this is where I want to start talking about, things like proton flux and electron flux effects. So Spooky One was deployed in 2019, right, from the International Space Station, and is still operational today. And the altitude of the satellite has fallen from 415 kilometers to about 360 kilometers. From the orbital predictions, we expect Spooky One to be in space for another 4 to 6 weeks before it will return to the atmosphere and burn up. And so if you're paying attention in the last slide, we reported that we have been successful in generating the quantum signals in space in 2019. And what have we been doing since then is that we have been studying the effects of accumulated radiation damage on the detectors. And we believe that this radiation damage comes from two sources, right? Essentially, one is from high energy protons, and the other one is from the electron flux in space, which contributes to a total ionizing dose. And how do we actually tell that there is collective damage being increased? Well, it turns out that if you have any semiconductor detector, right, what you're going to look for is that if you switch off every other light source in the vicinity of the detector and you just look at the current, right, that's coming out of the detector, you can actually see that it generates a signal. In terms of a photon counter, this means that it will give you a click even if there's no photon falling on it. So we call these events that are coming out of the detector dark counts, right? These are counting events that happen even in absolute darkness. Now, because of the quality of the manufacturing process, you can never get rid of these dark events or dark counts. So even at a perfect device that has just been shipped to you from the factory, if you were to measure it in the dark, it will always give you some nominal rate of dark count. But what we know is that if there's radiation damage, this dark count rate is going to increase, right? And so what we've been doing over the life of Spooky One is to look at this dark count damage at different temperatures, right? And over here, I plotted for you the results from 3 different temperatures, 1 degree Celsius, 5 degrees Celsius, and 10 degrees Celsius. And at all these temperature measurement points, we see that there's a consistent increase in this dark count, right, with time. And this, corresponds to accumulated damage. What's also very interesting is that we've noticed that in the first part of the graphs, there is a steeper rate of accumulation of dark counts, and then it sort of levels off, right? And you look at where this transition point in the gradients happen, they seem to happen also between 400 to 500 days. And it sort of corresponds to a point where Spooky started to drop much more rapidly towards the Earth. So this is something that we're still testing and we're still modeling, but it's actually very interesting. And it tells you that if you started to work perhaps below 390 kilometers altitude, you might actually be seeing a very slow rate of accumulation of radiation damage. This is something that we would like to understand better, right? Because if this was true and this was confirmed, we may have to think of ways of deploying satellites at lower altitudes, trading off against the fact that the atmosphere is actually thicker, and so the satellites will have exponentially shorter lifetime. And so that might actually require a further improvement to the satellite systems. For example, you might want to put on thrusters that can help the satellite to maintain its altitude at a 390 kilometer regime. So this is actually, an interesting observation that our team has done over the last 600 days or so. Now, I just want to spend the next few minutes talking a little bit about the detector physics itself, right? The single photon detectors that we use on the satellite typically look like this. There's a can, right? And inside the can, there is some device like a thermoelectric cooler with which you can cool or heat the detector. And the actual active area on this detector is this little black spot in the center over here. And then if you were to look at the internals of such a detector, right, you'll find that there are different doping regions of the semiconductor, whether they're p-doped or n-doped. And essentially what's happening is that if there was a photon falling into the active region, right, it will actually generate something known as an electron-hole pair, right? So typically what's happening is that the photon has sufficient energy that when it gets deposited in the semiconductor, it liberates an electron from the lattice, right? And so the empty site in the lattice is known as a hole. And then the electron itself gets promoted into something called the conduction band. Now, to understand actually how the detector is working, right, I have a little cartoon picture that I sketched out over here. So you can think of the different doping regions, right, the P and N regions as having different energy levels, but there's always a relative gap, right, in the energy. So at the top, we call this the conduction band, so that any electron that's sufficient energy to be existing in this region is free to flow through the lattice. Whereas if not, it will be trapped inside the lower region known as the valence band. So when a photon comes in, it liberates this electron and this hole, right? And then this electron is now free to move inside the conduction band. And the whole idea of detecting a single photon is that you apply a strong voltage across the detector such that any electron that's liberated would move very fast, right? It'll pick up lots of energy because it's seeing an electric field. But the semiconductor lattice is not perfect. So at some point, this electron is going to smack into the other atoms inside the lattice, right? And it's going to lose energy. Now, the idea is that if you have an electric field applied across this region that's strong enough, the electron will pick up sufficient energy that when it smacks into another atom, it might lose its energy, but it will then liberate another electron. So another electron hole pair is created. So the way we count these detectors, right, is by this avalanche process. So one electron that's free gains enough energy, liberates another electron. Now you have 2 electrons, then they go off to gain enough energy to liberate more and more electrons. And then you get a runaway process. And then your conventional electronics is able to detect the presence of a single photon. And this is actually how we convert quantum signals into electrical signals that we can actually process. So why is this picture important, right? This picture is important because if this was a perfect device, the gap between the conduction and valence bands would be completely empty, right? There would be nothing in between. So only in very rare instances would an electron gain sufficient energy from the lattice to actually hit the conduction band, right? However, what happens in a radiation environment is that, as protons come in, as electrons come in, and these are high energy particles, they might actually displace, the atoms inside the semiconductor lattice. And so you can think of the silicon atoms, right, being displaced. And when they're displaced, what's happening is that there are intermediate energy levels being created. And this happens inside the gap. So now, any electron that gains a little bit of energy has a sort of a ladder with which it can climb to reach the conduction band. And then it will actually create an avalanche that we can count. And this is the main reason why, even in absolute darkness, right, we see that the detector starts to give more and more dark counts as time goes by. And this is because more and more damage is being incurred inside the semiconductor lattice. So we have to worry about these effects. We have to think about how to shield against the proton or electron radiation flux that's coming into the device. If shielding is not possible, we have to think of other ways to try and fix that damage. And so we have been doing some testing, actually. So these photos are from some of our original testing at a proton facility in UC Davis in California. And so we had some of this electronics board that we made up, and we went to UC Davis. They had a proton accelerator, and they could actually expose, all our electronic components, including the detectors, against to this proton to see what kind of damage it was accumulated. And so from this exercise back in 2012, we were actually quite confident that most of the electronics we were planning to use would survive low Earth orbit conditions. And it was only the detectors that were susceptible to this increasing damage. And so we started to think of how we could actually improve the damage or correct for this damage. And so first I want to ask you to look at this graph over here, right? And we have a way of calculating the damage induced by the protons. We call it the DDD, or displacement damage dose. And as you can see that as the DDD increases, the dark count rate, right, which is a way of inferring damage, also increases, right? So this would be, before radiation, all the different detectors, these black spots, right? There's a scatter, they're about the same background rate. After radiation, you can see that they increase, and after a certain point, they say that they saturate, but actually they don't saturate. What's happening over here is that the counting electronics cannot keep up with the rate at which the dark counts are being created, and so they count to a maximum rate. Now, then what we realized was that you could take these devices, you could pop them in an oven, say heat them up to about 80 degrees Celsius for a few hours, and you can see what happens. And at relatively low damage rates, one could see that you could actually cause the intrinsic dark counts to actually drop. Okay, so this is a very good sign that you're annealing it, right? So it means that you are heating up the device such that the silicon atoms that have been displaced are moving back to the original lattice sites, and thereby removing this energy step ladder for the electrons to get promoted. So this is a very interesting aspect of it. The other aspect was that we noticed that even for devices that have been irradiated by quite a bit, if you cool them, right, you cool them to about minus 20 degrees Celsius, then the dark count rates begin to come down, maybe even to the original dark count rates. And the reason for this, right, is because now the electrons that would have caused your dark events, right, these are thermal electrons. If your entire lattice is very cool, then you have a much lower probability of the electron gaining enough energy to spontaneously get into the conduction band, right? So we have reported this in a paper, right, about how to actually heat up, the detector to remove the radiation damage. And more recently, some of our colleagues in Canada did a similar experiment, but instead of using a conventional heater, they shone a laser onto the detector. And so they did heating by optical absorption, and they could also demonstrate that there was annealing as well. So this is actually very exciting. So the quantum community, because of the requirement to work with the single photon detectors, we are starting to think of how to fix the damage that's caused by radiation. And so I guess I just want to end here and say that in this graph, we are now making use of the intrinsic heater that's inside this detector cans. And we've been building circuits that can allow us to heat up the detector for annealing or to cool it for operations, so that when we're operating it, we see minimal effects of the radiation damage. And that's all I have to say about my particular research. And I just want to point out to everyone that in the next few years, we do expect to see more quantum technologies being reported from space. Okay, there's all kinds of cold atom experiments on the ISS, and more exciting, quantum communication experiments being planned for many countries. And so with that, I just want to thank everyone for your attention. And if you want to find out more about our research, you can come to this website over here. I hope you guys, got a flavor of how quantum technologies is important for the future and why we want to put it in space, and how we're trying to mitigate the effects of radiation damage. Okay, Jillian, back to you.
Thank you, Prof. Ling. So we have a couple of questions in the Q&A. The first one is from Ashley. She asked, how does the MISIUS facilitate teleportation? I'm assuming she's asking what does it mean by quantum teleportation when you talk about that. Is it of the photons? She follows up with, instead of Star Trek, I mean. But yes.
Yeah, so teleportation is a very neat concept. I mean, of course, we're all familiar with the Star Trek teleportation, where you are transferring matter, right? So matter appears in one place and then it disappears in another place. What we're doing in quantum information when we talk about teleportation is that we are making the claim that even if you don't transfer the matter itself, you can transfer the state of the matter. So imagine that you have a collection of atoms, right, in a particular state. You could measure the information content of each individual atom and then transfer that information across to a distant location, right? Then you would have recreated the state of matter, right? Of course, during your measurement process, you are destroying that state in its original location, but then you're transferring it and recreating it somewhere else. So we call this teleportation, and it is the transfer of the state at a very fundamental level, right? We can't do this for more than one or two particles using today's technology. So what MISIUS did when they facilitated teleportation was that they transferred the state of one photon on the ground, right? They destroyed it, and then they recreated that state on the satellite, okay? And so this is actually the teleportation that they did. Now, this might not seem very exciting because it's not the transfer of matter itself, but it has a lot of implications on communication security. So in that sense, this is still a breakthrough experiment which could have lots of interesting and important applications.
Thank you. We have a question from an anonymous attendee. So since we just talked about gallium nitride, is it used just because of radiation shielding, or are there other uses for it, or are there other purposes for using gallium nitride as well?
Right. So gallium nitride is a semiconductor that is being used to build lots of new electronic equipment. And it turns out that gallium nitride, if you dope it correctly, it can also be used to build lasers. And so the particular laser that we are working with, it produces blue light at 4 or 5 nanometers, is based on a gallium nitride device. Now, it just turns out that, fortuitously, gallium nitride is known to be, quite hard against radiation damage. So even if you blast protons at it, it doesn't seem to, suffer from this displacement of the atoms inside its lattice. And so in that sense, gallium nitride is pretty good for building electronics that you want to work in space. We did not choose it just because of any shielding effects.
Okay. Next question asks, were the data shown collected from low Earth orbit within Earth's magnetosphere?
That's right. So all the Earth, you need to remember the data that we have been collecting, let's see, is when the satellite was deployed from the International Space Station. So when you send your nanosatellite out of the space station, they're always deployed below the space station, right? They don't shoot it up to a higher altitude, because then there's a chance that the satellite, as it comes down lower, it might smash into the space station. So they always make it lower. So everything we have observed comes from 420 kilometers or so, and starting from there. So this is where all the data has been collected from. Now, in terms of optical comms, though, we don't want to be putting the satellite too far away anyway. This is because the further your transmitter is away from your receiver, the more the signal will spread out. And so if you're talking about quantum communication in particular, where you are sending out individual particles of light and you want to receive each of those particles, having a signal that's diffracted, right? Technically, this is known as diffraction. And if it's diffracted too much, your collector, which is a telescope on the Earth, it's still very small. So most of your signal is going to be lost. So what we would like to do actually is to try and find ways to deploy the satellite transmitter closer and closer to the Earth's surface. The closer it is, the more of an advantage you have. Now, I think engineers will call this space loss, right? Because of the diffraction effect. And so if you're closer, your diffraction spot is just smaller. So you'll collect more of it into your receiver. So this is something that we have to keep in mind when we plan missions like this.
We have a next question that says, what's the difference between this and electrolysis? I'm sorry, whoever asked that question, I'm not sure what this is referring to exactly. If you don't mind, you could kind of elaborate a bit in the chat.
Yeah, maybe we can elaborate a little bit. I'm not completely understanding this question, but we can move on to Ayan's question, I see.
Yeah, is this communication on at all time? I assume like talking about like the quantum.
Yes, that's a great question, right? So in conventional communications, we want everything to be on demand, right? But when you think about quantum key distribution, what you're trying to do over there is you're trying to make sure that the end user gets an encryption key, right? And this encryption key can be, plugged into a symmetric encryption engine, and it can be used multiple times. And so what's important is that you want to allow the end users to build up a buffer of the secret keys, and then they will slowly consume the buffer. So in that sense, quantum key distribution type of communication doesn't have to be on demand. It doesn't have to be on all the time. And that's why when it comes to satellite quantum communications, what's important is that you need to have a good model of the atmospheric effects of your receiver, right? If your receiver is on a mountaintop or it's in the desert, then you have a really high chance that every time the satellite comes overhead, you can actually carry out quantum key distribution. If you are at sea level in a tropical climate like Singapore, where it's cloudy for lots of the year, you have to play a statistical game and try and identify, when is the best time to operate a satellite QKD, operation. Is it during the day? Is it during the night? Which period of, statistically, what would give you a better atmospheric conditions? So this is actually quite interesting. There's lots of research to be done. And this has implications not only just for quantum communications, but laser communications from space in general.
So we're a bit short on time, so I'm going to speed through some of the questions and see if I can combine some of them.
Okay.
So someone asked, I do not know much about material science, but isn't annealing usually done to reset ductility? Why is it done with the semiconductor in this context? Is no co-work necessary, and how long did it take to recrystallize the semiconductor?
Yeah, so you can do annealing in different contexts, right? The annealing that we are doing over here is that we're not really concerned about recrystallization or anything, because the damage is at really, at the atomic level. What we're trying to do over here is give the atoms enough energy, right? So that they just move slightly back into the original lattice size. So that's what we mean by annealing. I know there's other kinds of annealing that you do that you want to, like, smoothen out the atomic layering at the surfaces and things like that. But I do not expect us to be, going to that regime. The annealing temperatures that we work with are typically not more than 80 degrees Celsius. Why 80 degrees Celsius? Because the manufacturer recommends that you do not keep your detectors above that temperature, right? And in fact, we've also have a lot of evidence that when you take a detector, right, and you expose it to radiation damage, and you just keep it at room temperature, some of the damage will just spontaneously go away. So it's annealing itself even at room temperature. What we're doing is we're just giving it, a speed up in the annealing process by heating it up to 80 degrees Celsius.
Mikhail asks, are there goals to expand to continuous variable cell-like communications, amplitude and or phase modulation, or general laser quadrature modulation instead of teleportation or entanglement?
Yeah, so that's a real expert question. I think these are all interesting, techniques. There are groups around the world that's looking at continuous variable communications. I think there was a really nice German demonstration a few years ago where they reported that a satellite in geostationary orbit, 36,000 kilometers away, could actually be used for continuous variable quantum communication. The satellite was deployed some years ago, so it didn't have all the equipment necessary to do a foolproof quantum communication experiment. But just by measuring the amount of noise in the signal, they showed that in principle, by adding this additional equipment, it would be able to do this continuous variable experiment. So that's an interesting, technology that we should look forward to. I think there will definitely be some experiments in that direction in the next 5 to 10 years. So we have to watch out for it.
The next question asks, is blockchain better for encryption or quantum key distribution? Or maybe more likely, like what missions would prefer blockchain for encryption versus quantum key distribution?
Yeah, I would say blockchain uses encryption, right? And blockchain by itself is not an encryption process. But what's important is that blockchain would benefit from having encryption processes that are quantum safe. And so the question would be, is it better to do PQC, post-quantum cryptography algorithms, or to use QKD for blockchain? I think that's an open question. Lots of people are trying now to understand, that once you have a QKD appliance or PQC appliance, how do you actually plug that into the existing crypto infrastructure so that you can actually, enjoy its benefits and apply it to things like blockchain?
Yong asks, in Spooky 1, could your team use dark counts to determine an accurate radiation count? And if so, do you think this method could be applied to larger SIO lasers?
I'm not sure whether one could actually use it to determine accurate radiation counts. This is quite tricky because you have to calibrate the devices. So I would be a bit wary of saying that the single photon detectors are good for detecting like the amount of flux that you're observing. But maybe I will be proven wrong. Maybe someone in the audience is smart enough to come up with a technique for doing that. In fact, I think typically what we do know is that the radiation counters have a different architecture and a different design from the single photon detectors, because the single photon detectors are designed to optimize quantum efficiency, the conversion of a photon into an electron hole pair. That's what they're designed to do, and they're not so much designed to detect the presence of charged particles. But having said that, semiconductor devices could be designed in general, right, such that they become a detector of radiation. Because when these high energy particles go through the semiconductor, they do create, how should I put it this way? They do create lots of charged particles itself. And if you are applying a strong electric field over it, right, then you'll get an avalanche process. I think the devil is in the details. You have to calibrate the energy of this particles passing through the material with the amount of charge that's created in the avalanche. And if you can do that accurately, then you should be able to have a nice radiation detector. But that's just an idea. Yeah.
So I'm going to combine two questions together. What is the predicted computing power of a quantum computer in comparison to a traditional computer? And how soon can we expect to see quantum technologies intensively used in space exploration?
That's a good question. So the first question is a bit easier. I think we have to keep in mind, a quantum computer is not going to replace your conventional computer, right? The conventional computer is very good at what we're doing today, but the quantum computer will come in to solve problems that a conventional computer is not good at. So what are some of these problems? Well, putting aside the factorization of products of prime numbers, quantum computer can be good at sorting out an unstructured database, right? It's good at optimizing complex problems. For example, if you have what we call the traveling salesman problem, right? What's the shortest path between multiple points? A quantum computer actually has been shown to have advantage in things like that. And of course, finally, when you're talking about understanding protein folding or molecules, these molecules and proteins, they are actually quantum systems themselves. You can build an analog of this on the quantum computer. You can simulate these proteins and molecules very efficiently. And this is why quite a few people are interested in the quantum simulator, using a quantum computer to simulate these chemicals, because if you do make a breakthrough, you will have lots of impact on sustainability research, finding new materials, finding new drugs. So that's actually a very exciting field. Now, when can we see quantum technologies used in space actively? I guess when it comes to communication, we will be seeing, the devices around where humans live, right? Because humans want to communicate privately and securely, so we'll be using that technology for that. In terms of deep space exploration research, it is possible that as we build better quantum sensors, we may be able to deploy them on satellites so that they can actually, for example, be very sensitive as an accelerometer, right? Or a gyroscope, so that they can orientate themselves very, very precisely. And this is going to be important if you want to do communications over long ranges. Imagine you want to do Mars to Earth, optical communication. You will have to point your laser very, very precisely. And if you have a quantum gyroscope that can actually help you do that, it would be, very impactful in that domain.
Stephen asks, Let's say you transmit a photo from Spooky to the receiver on the ground. Can we assume teleportation will solve the problem of signal disruption due to ionospheric blackout or scintillation?
Right. So what's important in this case, right, is that the photon, which is your quantum system, needs to make it through the atmosphere into the receiver, right? If that's done, then in general, you have achieved quantum communication for that particular system. Now, whether or not you're going to solve the problem of signal disruption to the ionosphere, it's tricky. I think what we have seen at the moment is that the quantum signals encoded in light as photons, right? They don't seem to be affected by the atmosphere or the ionosphere. They seem to go straight through unaffected. But having said that, no one's actually, run a quantum communications experiment through a solar storm. So that's still a little bit out there. I'm not completely sure what will happen then. But I think in most cases, it will go through the atmosphere with little effects.
So we have a question I think they're from the same person, but how can quantum technologies, or is there a place for quantum technologies in biological research or the study of biological organisms?
Yes, so I think definitely when you talk about building a better quantum sensor, right? You can build sensors that are sensitive to magnetic fields, electric fields. They can be very, very sensitive. So when it comes to biological experiments, you may want to detect the presence of electric fields or magnetic fields inside a biological sample, and the quantum sensor can actually be very good. In fact, one of my colleagues at NTU, he won an Ig Nobel Prize for applying a quantum sensor to the study of cockroaches. So what he did was, he built this really sensitive sensor of magnetic fields, and it turns out that for some strange reason, cockroaches are slightly magnetic, and if they die, the magnetic field in the cockroaches would slowly degrade. And by using his really sensitive quantum sensor, he could actually, tell the difference between whether a cockroach was dead or alive. So he got an Ig Nobel Prize for that. That was actually quite funny.
Okay, we are running a little bit low on out of time, so I'll just ask one last question. Someone asked, what would it take for them to get a position to work with you on your team?
So I see a question. Does everyone need a PhD degree to work with my team?
PhD degree to work in your team.
No, you don't. So half my team are not even physicists. Half my team are engineers and computer scientists. Because if you're building a space mission, you want to put together different expertise, right? The physicists would be doing the systems design, but then in order to implement the different subsystems, you need people with mechanical engineering background, or electronics, FPGA programming, software programming. So there's actually a whole range of skills that's required. And this is only going to be expected as we start to move quantum technologies out of the lab. And if you want to build real world devices, you're going to have to build all this other enabling technology as well. So, if any of you are in Singapore and would like to, have an internship, feel free to drop me a line. But if you want to study physics with me in NUS, you guys are also welcome.
Okay, so with that, I think we can come to an end of the webinar. Thank you again to Prof. Ling for the very insightful session. I think there's a bunch of compliments coming in the chat. If anyone wants to find out more about what CQT is doing, I am sharing the link again in the chat, so you guys can visit the site and then also kind of reach out to them if you have any more questions about what they're doing and what they're working on. But yeah, thank you everyone for joining us today. I hope it was beneficial for you guys. And maybe you learn a bit more about quantum and how you might be able to integrate it into your challenge proposal when you're doing your projects. But yes, thank you everyone, and thank you again to Prof. Ling.
Thanks, everyone. It was a pleasure.